So when calculating Q, you have the option of a positive or negative value. In the previous problem, the value was positive. Okay, it was positive because energy was being absorbed by the water in the swimming pool. In this case, the water in the swimming pool was defined as the system. Essentially, the part of the universe we are focused on when talking in that problem. It's what we're looking at and what we're considering. Okay? So that swimming pool was our world, and that world was absorbing energy, and therefore, from the point of view of the swimming pool, the reaction was endothermic. On the other hand, you could also look at the surroundings in terms of where was the energy coming from. That energy had to come from somewhere, okay? And this is the rest of the universe. And in the previous problem, in this case, it would have been the air or the sun or something in the surroundings that were providing the energy to that system. And from the point of view of the surroundings, the process would be exothermic. Generally, we're looking at things from the point of view of our system. Okay, the system in this case was gaining energy. But you have to understand that when you consider whether something is losing or gaining energy, you are generally considered the surroundings. If I were to stand somewhere and hold in my hands a beaker, and that beaker were to feel warm to me, that would suggest that I am gaining energy from the beaker. And if I'm gaining energy from the beaker, I am experiencing an endothermic process, and what's happening in the beaker is in fact exothermic. If, on the other hand, I was holding something in that beaker and that beaker felt cold to me, that means I am giving energy to the beaker. And what's happening in the beaker is in fact endothermic. So I normally would like you to consider that you are an observer. You are part of the surroundings. If I hold my hands up to a campfire and I feel warm, that means the fire is giving energy to me. Therefore, I'm feeling warmth and the fire is releasing that warmth. Okay, let's do 2 more slides for this part of the presentation. This is a diagram of what is called a bomb calorimeter. Really isn't a bomb, so it's not quite as dramatic as the name sounds. What happens is in the little compartment that you see here, a sample of something is attached to some ignition wires and basically exploded, burned very quickly. It's not really a bomb, but it's burned in some oxygen very quickly. And so what happens is heat radiates out of this little chamber into the surrounding water, and the stirrer here rotates the water so the heat is absorbed evenly, and then the thermometer measures a delta T, and in this case the delta T is measured for the entire calorimeter. All right, the device itself, the water, the stirrer, the compartment inside, all of this contributes to absorbing the energy. And so instead of using the Q equals MC delta T equation, okay, we just simply use the heat capacity of the calorimeter, which is joules per Kelvin, multiplied by the delta T. And that gives the joules generally released in the combustion. And so this is usually reserved for an exothermic process that makes the temperature of the water increase. And in this example, we have a sample of a compound called methylhydrazine, which is this compound right here, is combusted in the bomb calorimeter. The temperature of the water and the calorimeter goes up, and the heat capacity of the calorimeter has been determined to be 7.794 kilojoules per degree Celsius. Now notice, in this particular example, they're giving you the heat capacity of the calorimeter per Celsius. Totally fine, all right? Doesn't matter, work with the units that are given. Convert to Kelvin if you want, but there really isn't any need to. As you recall, delta T is equal in Kelvin and Celsius. And so all we need to do is multiply this by the delta T, which is 14.50 degrees Celsius. Okay? And that calculates to 113.0 kilojoules. I'm maintaining the 4 significant figures that are present in both of my values. This value is 4 sig figs. The delta T is 4 sig figs. And so I'm keeping a 4 significant figure answer. Okay? Now, we're not done, because they wanted the heat of the reaction for a mole of methylhydrazine. So we have to take this value here. We had 113.0 kilojoules. That was for a 4-gram sample of methylhydrazine. And 1 mole of methylhydrazine has a mass of 46.0 grams. I guess I could do that to 4 sig figs, and probably should. Let me recalculate that. 46.06 grams per mole if we want to maintain 4 sig figs. And my final value is 1301 kilojoules per mole. And that could be called the heat of the combustion. Heat of combustion of 1 mole of methylhydrazine.